Today I'd like to solve an interesting little problem in structural analysis that might give you, initially at least, a surprising result. So imagine a simply supported beam of length L subject to a uniformly distributed bending moment. This is not a torsional moment, this is a bending moment. Okay? Simply supported beam subject to a uniform bending moment of magnitude lowercase m. If we simply compute the reactions on this, we are going to find, as it should be, that we have two opposite vertical forces at the two ends, and they are going to be equal to what? Well, the total moment by this is equals to lowercase m times the length L. Right? So then these reactions are going to be ml divided by L. So actually the value of this is lowercase m, which makes sense because m is in the units of moment divided by length, which would be something like kilonewtons meter per meter, right? So the units that come out are actually units of force. So with these reactions, we can then go ahead and compute our moment diagram and shear diagram. So if we are here, we have this reaction here going down equal to lowercase m, this reaction here going up, lowercase m, and if we make a cut anywhere here at a distance x from the left support, what we find is that, right, we find here shear moment, this distance is x, and we have our uniformly distributed bending moments here, lowercase m. Well, if you do that, you find out that the shear equals to what? Minus m. Right? This has to go up, so minus m. However, the moment at any point x is going to be equal to what? Well, m times x and m times x, but in the opposite direction, right? So m times x going this way, this one is moment per unit length times length, m going the other way, so the moment is 0. So here is an interesting case where the equation for the bending moment is not equal to the integral of the shear as it is usually presented in most structural analysis books. So the question is why? We have done everything correctly, everything is fairly straightforward, so how come these two don't obey the typical relationship that the derivative of the moment equals the shear, or similarly the integral of the shear equals the moment equation? Why does that happen? Think about it for a little bit, and I'm going to post another video answering this question.